Greetings again, AP Calculus AP students. Mr. Record here from Avon High School, taking a look at example 4 in our video series over topic 4.2, particle motion, connecting position, velocity and acceleration. And we have another bug on our hands. We're going to be looking at another velocity graph of the motion of a bug, and we're going to answer several questions. This is a calculator active problem, so if you've got a calculator handy, you might want to grab it in case that you want to follow along. So let's take a look and see what example 4 has in store for us. Once again, I want to thank my good friend Brian Passwater for another wonderful problem. Let me move my camera down here so we can not cover up our good friend. This is our bug, Hiram. Hiram's going to do a little walking here for us. So we've got this time interval 0 to 2, and Hiram, our bug, is going to move along the x-axis, and he's got a very interesting velocity graph and a velocity equation. It's a very ugly equation. V of t is equal to t squared times sine of the quantity t cubed minus 1.5t. Apparently that is what the graph of velocity looks like. So what we're going to do is answer several questions. First of all, we're going to find a of 0.7, and we're going to ask if the bug is speeding up or slowing down at time 0.7. And of course, we're going to have to explain our reasoning just a little bit there. So let's go ahead and tackle our part A first. Now, we're asked to find a of 0.7. So that is exactly where we're going to start. A of 0.7. And the only way that we can find that is to take the derivative of our velocity right there, and we could say that that is certainly a true fact. And the only thing that we have now is to actually find it. And I got a feeling we're probably going to be approximating it. We'll see what it looks like on the calculator here in a second. But let's go ahead and let's make that happen. So I'm going to move to the calculator right now and show you how to do this. All right, so we find ourselves using a calculator. I'm going to use the TI Inspire to show you how to do this. There's a variety of ways to do this on other calculator models that aren't too very difficult to figure out. But I'm going to show you how to do this a little bit more efficiently for you TI Inspire users. One of the things that I like to do in a free response question that might very likely refer back to the same equation time and time again. We're only on part A, so it's very likely we're going to be doing some more things with this velocity equation as we move through the problem, is I like to define our function. And you know that our function was called v of t. To define a function, you would hit your control button followed by the math template, and you'll notice that that brings up that colon equal. So that means that we're going to store this equation. And that equation is v of t equal t squared. We multiply that by the sine of the quantity t to the third power, and we subtract 1.5t. And then once I hit enter, I'm going to get this word done, which means that that function v of t is now stored into the calculator, which is pretty cool because we don't have to type it in anymore. In fact, if I were to type in the letter V, we can see that it's bold, non-italicized, which means I could figure out values. If I wanted to plug 2.4 in for t, I'm going to get an answer. And so it's a little bit more convenient, and it's always going to stay in our calculator. Now, remember, we're looking for the acceleration at time 0.7. So what that means is we're going to have to take the derivative of this. One of the quickest ways to do that, I think, is using menu, calculus, and derivative at a point. Those of you that use the TI-84, that's your math 8. When we get into this menu, we can say our independent variable is t in this case. Our value that we're trying to find the derivative at is 0.7, and of course we want the first derivative. So it's going to set up our template here, and all we have to do is type in v of t. And so we hit enter, and boom, we have the answer that we're looking for. We're going to call this negative 0.92. I'll call it 0.5. Let's go to 4 decimal places so that we can be as accurate as possible. So we are back here in our document, and we're going to go ahead and use an approximately symbol and write that particular value. I think it was negative 0.9205. Right? I like to use approximately because I know that I had to truncate that. Okay, now the next part of the question, is this bug speeding up or slowing down at time 0.7? This is where you're going to have to start thinking about some of the things that we mentioned previous to this particular video. A particle speeds up or slows down depending on the signs of the velocity and the acceleration. So in other words, if we know that we have an acceleration that's negative, we're halfway there. We're going to have to figure out what is the sign of the velocity. And so you're going to have to do the velocity at time 0.7. And so we're going to have to return to our calculator to make that particular calculation. So again, we're going to benefit from having stored our V because when I type in V, it's bold, it's being recognized. I just enter my time 0.7 and boom, there I have it, negative 0.3182. Let's go ahead and truncate that. So we're going to go ahead and call that approximately negative 0.3182. Now that we have both our values of A and V, remember speeding up means that your signs are the same. Slowing down means your signs are opposite. And we're talking about the sign of the velocity and acceleration. Here we see that both of them have the same sign. So basically what's happening is that this bug is moving to the left because of the velocity of the velocity that's negative, and the velocity of the acceleration sign, sorry, is negative as well, means that force is pulling it left even faster. And so we'll say that very result, oops, go back to the document here. So we're going to say the bug is speeding up. Now it does want you to give a bit of an explanation. So we'll just simply say the bug is speeding up because we don't have to reference the exact value. All we have to do is mention that their signs are what they are. And I think that would do a good job. And we're done. Of course, you could say some more things like the bug is speeding up at time t equals 0.7. Some of those extra little phrases that you throw in there add a little bit more clarity, but the things that we're looking for at the reading is definitively, are you saying the answer as speeding up or slowing down, and are you giving us enough justification? The fact that A and V are the same sign alone would be enough in this case. All right, let's take a look at part B. Find any values of t in the interval 1 to 2 when the bug is at rest. So you have to be thinking, translate into a different language. Let's go from English into calculus. A bug is at rest has the same meaning as velocity being equivalent to 0. So you just simply have to find out where the graph of this particular velocity is equal to 0. And it looks like there's a couple of times, especially between 1 and 2. Now, there are a couple of different ways to do this. I'm going to go ahead and show you both ways. One of them will not apply to anyone who does not have a TI Nspire CAS calculator. The other one is much more universal. So let's return to our calculator and see what we've got here. If you have a CAS calculator, which would be your TI Nspire CAS, maybe the TI-89, just to name a few models, you could certainly try to solve it using Algebra Solve. You're taking your V of t, saying when it's equal to 0 for the variable t, and I would very strongly encourage you to put your domain restriction. We want to find this such that 1 is less than, or t is less than, and you get your symbol, less than or equal to, I should say. You get your less than or equal to symbol by hitting Control equal, right? put a decimal in if you want decimal output, and sometimes you're going to get this stuff. Now, you could try to tweak this. Maybe if I put a decimal here after the 0, maybe that's going to be better. Oh, not so much better, right? Sometimes it's a little frustrating in the way that the calculator wants to render some answers. It's okay. We always have a backup plan if we're using a CAS calculator. And those of you who are using a TI-84 or maybe a TI-Inspire numeric, you're not going to be able to do this anyway. So the next way is the way that I really do like a little bit better. Now, it comes with a little bit of a drawback. We are going to have to graph this equation. I've already solved it or stored it as v of t. That's a bit of a problem because when we input our functions, we really want to be inputting them in terms of x. It makes it a lot easier to use our calculators. So there's a variety of things that you could do to change what our entry was in terms of x, but one of the easiest things I think to do for kids is just to tell them, it's okay, you can retype this in. It's not a big deal. Just make sure that you type it in accurately, and this would work fine. All right, whoops, let's make that a minus. There we go, now we're fine. Now, something to consider. What if I would have done that originally? Maybe I should have stored my original function and call it a v of x. That's kind of the direction I try to go towards the end of the year with my students, because you never know when you might want to take that stored equation and graph it. Because if we had stored it as v of x, we could have just entered v of x here and been okay. All right, we're going to go ahead and we are going to graph this. Make sure that you're in radian mode. You got a really interesting graph here, to say the least, but remember that we're only really concerned with what's happening on a very small interval. So I'm going to go into my menu, window, and window settings, and I can just change my x-axis, y-axis, mins and maxes to maybe accommodate the let's say the graph that I was given. I could go back to the document. You can see that it goes from about -1 to 2.5 along the x-axis and -4 to 3 along the y-axis. And I use increments of 1/2 on the x-axis. So let's see if we can make those things happen. So I go from -1 to 2.5, I think I said. And the scale for the x-axis looked like it was 1/2. And if you remember, I was -4 to 3 along the y-axis with a scale of 1. And that's going to give us a little bit more, I guess, normal view of what's happening with this particular bug. But if you really think about it, I've probably given you too much there. And the reason is because if I look back at the stem, I'm really only concerned with what's happening between 0 and 2. So anything outside of that you can get rid of. I'm not going to re-graph this for those purposes. I know that I crossed the x-axis 2 different times between 1 and 2, and I'm going to find them by using my menu, analyze graph, and 0, which is the first option up there. On the TI-Inspire, you just simply move your little lower boundary bar left of the first intersection, hit enter, and then slide it to the right, and then boom, it's going to pick up your first intersection. Now remember, you might have your calculator set up where it doesn't give enough decimal places here. You definitely want to fix that. Hover over it, hit the plus button, it'll add a couple more for you, and then just repeat the process. Menu, analyze graph, 0, move this to the left, hit enter, slide it over to the right, boom, it's going to pick up the next one, and I would hover over that guy as well so you get some more decimals. So our answer is going to be 1.2247 and 2.1146. So let's return to our document and let's write up that solution. You don't have to write a sentence here, but I'm going to go ahead and do that. The bug is at rest when v of t is equal to 0. And this this occurs at. I like the idea of you saying v of t is equal to 0. And the reason is because you don't want to give a bald answer. You don't want to just write t equal approximately 1.2247 and t is approximately, what do we say, 1.80. Let's double check that. Oops. You know what? I wasn't paying attention. I don't want that point. I want this one. That guy's out of the picture. Let's do this one more time. Menu, analyze graph, 0. It's like being on live here. Here, click that guy. Now, that's the one that I want. It's a good thing I was paying attention there. I'm not going to deny the fact that this bug was stopped at time 2.11. It's just that that's not in our interval, right? So 1.8012 we're going to call it. But as I was saying, you don't want to leave your answer bald. You don't want to just throw out those two t's. Talk about where they come from. A lot of times in my class, if a student makes an egregious calculator mistake and doesn't get these two answers correct, but on their paper they knew to set v of t equal to 0, they can earn a point. All right, we go down to part C now, and the question is find the open intervals on time 0 to 2 when the bug is moving to the right. Now, we talked about this in a previous problem. Moving to the right is the same thing as v of t being positive. Moving to the left is when v of t is negative. Stopped is when v of t is 0. So you just have to look at this graph and determine, well, when is this graph between 0 and 2 above the x-axis or the t-axis? And we can see that it would certainly lie on this particular stretch. And fortunately for us, I think we've already figured out what those two endpoints are going to be. And so we can just simply say, or restate, the bug moves right, or the bug is moving right, let's give us the reason why, and that would be when v of t is greater than 0. And then we can say which occurs. You can word it a lot of different ways. And since this is an interval, I'm going to use the word on. And then I'm just going to use the same two decimals. Again, you don't need all 4 decimal places. Again, the reason why I put 4 decimals is just so that in case I was going to use those to compute something else and express that answer to 3 digits, I just wanted it to be a little bit more accurate. All right, so we're going to go with that for our part C. We're about ready to wrap this up. We have one more part. Find the acceleration of the bug when v of t is -1. Well, when v of t is -1, well, that's going to be kind of interesting because we are actually going to want to solve this graph equation when v of t is -1. Now, visually, you could probably see, here's our graph of v of t, here's our -1. I'm going to put a little X here to mark the spot. That's when that's going to occur. Now, because we did not have a lot of success trying to solve the equation with CAS, I don't know if we want to go that direction. Trying to show off with your CAS model calculator may not be the best thing here. V of t equal -1. Let's not do that. Let's go back to the graph. Here's our graph. I can move these out of the way here just a little bit. And if this f1 of x is serving as our velocity equation, let's go ahead and put another equation in there that's equal to -1. There he is. And now you just want to figure out, where does the blue graph cross the red graph between time 0 and time 2, which is going to stop right here. So we only want this intersection. Okay. And again, I could have really done myself a big favor if I would have gone into the window settings and been a little bit more careful and maybe only graphed it from 0 to 2. Then you're not seeing all this other stuff that's not important and you're focused only on this point. So if I go into menu, analyze graph, we're now looking at intersection. We would choose the lower bound, there's only 2 graphs here. Those must be the 2 graphs we're finding the intersection from. So I'll click there, move it to the right, hit enter, or click my mouse here again, and that would be my intersection. And of course I can add more decimal places, and there it is, 1.836, or you could say 1.837. Now you want to be careful. Is that our final answer? Well, all we know is that v of t is equal to -1 when t is approximately that number, right? 1.8368 I think we had. Now here's our problem. That is not our answer, because the question says find the acceleration when v of t is equal to that. So what you're going to have to do is take that time and plug it in for your acceleration. And I'm going to go ahead and use all 4 decimal places. You don't necessarily have to write this again, although I think it's probably pretty powerful to do that. And then if you recall on our calculator, if we go back to the calculator page here, we can go ahead and compute that derivative. Same way as before. Menu, I want calculus, option 2, derivative at a point. T is going to be my independent variable. My value is that 1.8368, and I'm going to compute the first derivative, and my function was v of t. And I think I scrolled up a little bit there. There I go. Now I'm ready, and if I hit enter, that's going to be my answer right there, the -28.8726. I might just write that down here. And that would be your acceleration at that time. It's a negative acceleration, so it's just a force that's pulling this bug in the left direction. Anyway, I hope this helps a little bit more get familiar with these ideas of velocity, position, and acceleration as they relate to equations and graphs of velocity. We still have a few more videos to go in this particular series. It's rather one of our longer units, or topics, I'm sorry, within this unit, because so many applications of this occur on the AP exam. And as you expand your knowledge of calculus, maybe you move into a Calc BC course or a Calc 2 course later on, you're going to do even more with motion. So anyway, I hope this helps. Would love to see you at the next video. Take care.